Hello, welcome everyone. I'm Chance. In this lessons, I'm going to talk about the tension test. Okay, let's start without any delays. So in these presentations, in these lessons, first I'm going to briefly introduce about what is the tension test. Then I will move into what is the principle of tension test, and how the deformations could be occur in this tension test, and a little bit more into the fractional mechanics while we perform the tension tests, and then I will make a conclusion. So the first things we need to understand about what is tensions. I know very well you guys have watched already about this Squid Games movie. This is very famous movie. In this movie, there is two groups, all right? Two groups. They are applying the force on the strings. There is one group on the side, another group on the another side, right? So they are pulling these rods, okay, into the opposite directions. When you pulling these rods into the directions, there will be a tensions at the center of the points. So if you can see in these animations, right? So the force is acting onto the opposite direction, and there will be tensions at the center of this rock. Okay, this is about the tension. So I think you understand about what is the tensions, okay, on the material. So the tension test, why tension test is important. So these tension tests that we know it as a tensile test, this is very most common mechanical stress strain tests in the material science, but it's not material science, but also in the other field, very useful ones, very useful mechanical property. So this tension test provides the information about the property of the material, like the strength and ductility. Okay, this kind of property can be provided by using this stress strain test. Okay, so and this information is very useful when we do the comparing the material, the property of the material, and when we deploy these aligning elements, the aligns, and how we're going to increase the strength, how we can able to increase the ductility. So these kind of things, to engineering the material. So this mechanical stress strain test is very important. Okay, but that will be one thing that we need to keep in mind is that, okay, when we perform the test on the particular, okay, specimens taken from the material, so this is not representing the whole material. Again, this is not representing the whole material, but this kind of values can be given that can guarantee that this material have this kind of property that can pass this kind of strength, this kind of stability. Okay, so this is the very useful information that's giving the information and property of this material. So let's start with the specimens. Okay, so as I mentioned before, we take the specimen from the base material, but here is I'm not going to talk about the standard of the specimen, but I just want you to understand the shape and also how the nature of the specimens. But here I just want to point out, okay, there are two different types of specimens mostly. So we have a flat type specimen and a rounded type specimen. So the thing that I just want to point out is that, so there will be whatever the specimen it is, there will be whole length. Okay, this is the L represented by L, and there will be the reduced sections. So at the center length, there will be the reduction length, right? So this is the reduction length, so which is the A. Then the more important thing is the gauge length. So gauge length is the length that we have to keep in mind that is the most particular area that the strains will be acting on this area. So this is the gauge line. So when we do the calculating strain, so this area at this length, the length and the area from that length, it's very important to do the calculation of the strains. Okay, so the gauge length is very important to know, because we need to measure the gauge length before the test. So we need to measure the gauge length after the test, and then we can see what is the the elongations, what is the radiation area. So these kind of things can be calculated. Okay. So now we have the specimen. Then the specimen will be loaded to the tensile machine. So this is a tensile machine, and then the tensile machines. Okay, the specimen will be grid. Okay, by the tensile apparatus, and then there will be the extensometer that could able to detect the elongation of this material. Okay, so this kind of information can be provided by that one. Then, so when we put the applying force by the time I mentioned, so what they're going to happen is that the specimen will be stretched out and the stretching out, and at some points is going to be like a broken, okay, broken points. So this is the stress strain cause, and then by mean that, so we can calculate. So the stress H means like the applying force acting on the original the area or the specimens. So this is engineering stress. And another one is the strain. So the strain is how the change of the length, okay, before the tensile test, before after the tensile, okay, after the tensile test. So this is the engineering strain. So we need to keep in mind that it's important to think the stress strain cause, and then engineering stress and engineering strains. But different on the a different type of material. So these kind of stress and strain cause difference is because of the nature of material, the bonding of the material, the bonding of the atom in this material. So the metal, they have the very sharp piece, and then at some point is broken. So we can see like the pressure points is very clearly after we put the maximum load on the material. But like polymerase material, these pressure points is very difficult to determine because they just keep going well until at the highest points, and it's broken the highest point. It also the same principle on the concrete like cement material. The pressure point is given before the highest tensile, highest low of the tensile force. Okay, so different materials giving the different nature of the stress strain curve. So let's start talking about the principle of the tensile test. Okay, so first, so the material will give a particular force to the specimen. So from point A to the point B. So in this stage, okay, the strain and strain are proportional each other. And then as one particular point, there will be the limit of the elastic, okay, deformation. So this is called the elastic limit. In this range, there will be no deformation, okay? There will be no deformation, and you can see the specimen. Then after the point B, and we just keep giving the stress, the specimens, and then it's increased to the highest maximum load, and then at the point C, it's broken. So this is called the diffraction point. So there will be two regions, from region 1, which is the point A to point B, and the region 2 in the point B to point C. So the point A to point B, that we call it the elastic regions, and the points B to point C is the plastic regions. So this is how it's gonna be like when we do the tensile test on the specimen. So I just wanted to show you one simulation. That's when we do the tensile test on the specimens. So each stretching out acting on the whole line of residue section, and then at some points, and it was broken. So this is the principle of the tensile test. So let's take a look at more details. The first ones, which is the elastic deformation. So you guys know the rubber bands, right? The rubber bands have a very high elastic property, okay? Once you stretching out, with the applying force, and it's stretching out very well, very long, as long as you pull out of these rubber bands. And when you release these rubber bands, it's going back to the original shape. Okay, so the material that's able to go to the original shape after we apply the applying force, this is called high elastic property. Okay, high elastic property. So the deformation in which stress and strain are proportional is called the elastic deformations. Okay, the points that hit stress and strain are directly proportional to each other. Okay, this is called the elastic deformations. So when you release the applying loads on this material, on this particular specimen, so it can go back to the original shape. This is called the elastic deformation. So this is deformation. So in this case, stress and strain are directly proportional to each other. This is called a Hooke law. Okay, so and then by this means we can get the information about modulus of elasticity, which is the Young modulus, or the proportionality that we call it in many different ways. So this modulus of elasticity can be thought of a stiffness of a material. This is how the resistance of material to the elastic deformations. Okay, so this elastic deformation is non-permanent, and which means, as I already mentioned before, when you relieve the applied load, the piece will return to its original shape. Okay, but it is not just dirty proportional in all the material, but there's some kind of material that have like a little bit like a parabolic shape, parabolic nature. In that case, we need to use the secant modulus and the tangent modulus to know the modular for electricity. For example, like gray cast iron, concrete, and many polymer. So they don't have the the proportionality between stress and strain. So we need to use the either tangent or secant modulus to see the modular elasticity in these non-linear behavior of material. Okay. So in the atomic scale, what's going to happen once doing the elastic deformations? Okay. So in the atomic scale, okay, when the elastic chain is just like, it's like the small changes in the interatomic spacings and stretching of the interatomic bonds. Okay, when you're stretching out this material, it is not deforming. It is not deforming. It is just like you trying to stretch out, okay, interatomic spacing, the space between two atoms. Okay, so you trying to stretch out the length of the bonding between the two atoms. Okay, in the material, the length of the material between all the atoms. So this is the elastic deformation. So the magnitude of this electricity, the modular electricity, the Young modulus, is the measure of the resistance or the separation of adjacent atoms. So the stronger the bonding, the stronger the modulus of electricity. Okay, so this modulus, okay, can be measured the slow or interatomic force separation cost of the equilibrium spacing points. Okay, in this graph, okay, in graph, and you can see there will be weakly bonded material and also strongly bonded material. Okay, when you apply the loads, there will be the increase of the separations. So with the internal the radius between the two atoms, and then one big separation distance is increase. Okay, there will be formation of a curve, like a curve, and there will be the equilibrium a state or conditions which there is no force between, okay, the between two atoms, and this equilibrium curve. So if you want to know the the modular electricity of this material, then you can put the slopes on these equilibrium spacings between the atom, and then you can see like how the modular electricity of this material. That's why we can calculate theoretically about the material, the modular electricity of the material, depend using on the type, the bonding on the material. Okay, so that's why different material have a different modular for electricity, the electric modular. For example, ceramics, they have the highest modular for electricity because the bonding that they have is like covalent bonds, Zionist bonds. So these bonds are very strong. Okay, very strong. That's why if you want to do the stretch out this the bonding between the two material, you have to give the height force or height Young modular. So they have a height Young modular. Okay, for metal, yeah, they are binding metal is bonding. The electron are found in clouds around the metal, and then they are just a little bit more easily to be able to stretch out compared with the ceramides. The polymer, the very weak bonding. Actually, they also have a covalent bonding, so many different bonding. But the reason why they are very weakly is that it's because of the very amorphous, and also they are just like in the form, the chains are also different on the cross links or the branch of the polymerase shape, this kind of thing. For the composites, they are combining two different type of materials, depending on the type of material that you are mixing to give the nature of the Young modulus. Okay, and also this kind of Young moduli is depend on the environments, like it depend on the temperature. So once you increase the temperature, the Young modular for electricity will be decreased. Is it very simple concept? When you heat it as a material, the material will have a kinetic energy. So the electron around the electron will have just like, you know, movings, like vibrating, these kind of kinetic energy. So these kind of kinetic energies will decrease the modular of electricity very easy to be able to like suppress the bonding. Okay, so this is about what happens in the elastic deformation. So let's go next to the plastic deformation. So after the elastic deformation, there is points. Okay, there is a point of elastic point. Then after elastic points, so there will be the plastic deformation. So in these regions, the first one that we need to know is about the yieldings and the yield strengths. Okay, the point of yieldings is very important. So this is the initial departure from the linearity of stress and it's the initial departure from the elastic point. So after the elastic points, there will be the yieldings. So this is very difficult to identify the yield points. Okay, the yield points, but normally we using the offset points 0.002, these stress strain cards, and then I'm getting down into the planar and into the strains lines, and then we can see the yield strength of the material. But some kind of stress and strain card, there will be the upper yield points and lower yield points. So so this yielding points is very important because it's measure of the resistance to the plastic deformation. So Young modulus is the measure of the elastic deformations, but the yield strength is the measure of the plastic deformation. So we need to see clearly, okay, what the difference between the modular of elasticity and the yield strength. Then after the yielding points, so the loads will be increased to the particular maximum load, and then this maximum load, which is called the tensile, giving the tensile strength of this material. Okay, so until this point, the applied load is acting on the specimens, reduced section of the specimen uniformly. Okay, and then at this point there will be the formation of the nicking. So after this nickings, the stress will not be uniform. So the whole length, okay, is gonna be like the 1 points at the nicking points, clearly, okay, and then it's gonna be breakdowns of the final points. I will call the fresh points. Okay, so let's talk about what's gonna happen when we do the plastic deformation at the atomic scale. So plastic deformations is the breaking of the bones. Because elastic deformation is not breaking of the bones, but the strength of the bones. But plastic deformations, we're going to breaking of the bones, and then it's gonna be reformation of the bones with a neighbor. Okay, a large number of atom molecule. Okay, upon removal of the stress, and they are not going back to the original shapes because we already broke the bone between atom and then reforming the new bones. So there will be the new shape, the new nature of the material once we did the plastic deformation. So but this kind of deformations is depend on the crystalline or the amorphous material. Okay, for the crystalline solids, so deformation is accomplished by the process of slave, okay, slave system. This involves in different kind of the dislocation. But for the plastic deformations in the non-crystalline solids, it is becomes by means of the viscous flow mechanism. So for the crystalline surface, as I mentioned before, deformations by the slave system. So there is dislocation motion. So there will be two different main dislocations, which is as dislocation and screw dislocations. But some points, these dislocations will be mixed together and then found a dislocation. So these dislocations motions in this material, we call it the slits, okay? And also these dislocations will be moved into the material, along the material by means of the cis planes, and it's followed that the direction of the slit direction. So the combination of these direction and slit planes, this is called a slit system. Okay, slit system. So depending on the type of the crystal structure of the material, they have a different number of slit systems. For example, okay, FCC and BCC, they have relatively large number of slit systems. Minimum number is 12. Okay, so that's why there's giving the high delta nature of material. But for the ACP, has a connects cubic structure. So in this kind of structure, they have the pure slick systems. So that's why they're giving the beta. But I'm not going to much detail, but these slick systems are giving the nature that the deformations can go through into the slick system, into the defined slip planes with the direction. So the deformations can be occurred in this slit plane and direction. So the materials can go into the deformations by means in these slit systems, and then giving the nature of the delta. So this is what's going to happen, the plastic deformations at the atomic scale. So when we talk about the tensile material, tensile test, so ductility is very important. So ductility is the ability of the material that permanently deforms without breaking when its force is applied. So when talking about the ductility, there is two different indicator. That's we can use. The first one is Poisson elongation. So it's like a quantifying of the plastic deformations by measuring the distance between the gauge line before the test and after the test. So this is taken by the final lunch and the original lunch. Okay. The another one is Poisson reductions. The Poisson reduction area is the same principle, but this one is using how the lunch of the area in the original shades and the lunch of the area after the pressure point. So this is the two different indicator that we can use to define the ductility of the material. So next, let's go to the friction mechanics. This is the last point. The friction mechanics is very important to understand how the pressure could be occur when we do the applying force on the material until it is broken. Okay, the first one is the friction mechanics in the delta material. Okay, so in the simpler tensile test, so delta material start with the nucleations and growth and coalescence or the microbials. These microbials were nucleates at the beginning of the applying load, and then these microbials will be growth and then coalescence along the center of the test bar. Okay, so these microbials will be initially as found at the center of the test bar. When you apply the loads on the tensile test, and then it's gonna be growth and coalescence. This kind of process was going to be occur. So these microbials is found because the struts cause the separation of the metal at the grain boundary and also interface between the metal and also small impurity particle, just like inclusion. After that, there will be the slit. As one point of the tensile load, there will be the slit. That's gonna be occur when this resort shear stretch reach to the critical resort shear stretch, and also it's maybe because resort shear stretch are higher at the 45 angle to the applying stretch, what you can see in the figure. And then there will be the flat at the center of this fracture, final fracture, and then there will be slit like a 45-degree angle. It's just like the nature of the cap, right? So this kind of nature would be occur in the daytime fracture mechanics. So the daytime fracture normally occur in the nature of the triangular manner. So it's giving the high good ductility and also toughness. So as you can see in the figure, the illustrated figure, so the fracture, the red line is like the propagation of the crack. Okay, the crack is going through the grains. So that means we can say that by means of this axial image, giving the information about the triangular manner and giving the high ductility nature of the material. The second one, okay, and then to make it more clearly about the microstructure feature of the time fracture, that you can see at the center of the fracture point, there will be round equid dimple. Okay, round equid dimple, but on the slit direction, okay, slit planes like a 45-degree angle, there will be oval dimple. Okay, this is because these microbuoys are elongated at the slip planes. So as you can see in the figure A of this image, so there will be rounded shades at the center points of this fracture, but there will be elongated nature, the dimple, so on the slit plane. By mean that, so we can see this kind of material have a good ductility, and there will be the mechanic of the fracture is just like forming the microbuoys at the beginning of the points, and then this became the growth and coalescence until the fractures occur through the slit durations of the fracture mechanics. So the next one is the microstructure feature of the brittle fracture in the metallized material. In the brittle fracture, so there will be little or no plastic deformations is required. Okay, so the crust can easily progress along the specific crystallographic planes 100 by cleavage. Okay, but this kind of plane depends on the type of a material. But in some cases, the crust may be occurred by intergranular path. This intergranular path is caused by the segregations or maybe inclusions of the grain boundary. So as you can see in the figure, so the crust is along the grain boundary. So this is called the intergranular crack. Okay, so as you can see the image, so you can see the crust is occur in the along the grain boundary, and this is giving the nature of that high material at this applying load. Okay, and also there could be another fracture feature by means of chevrons patterns. Okay, this kind of pattern can be seen even by naked eye, but if you can use the magnifying glass to see very clear image of this, the fracture feature of the chevron patterns. Okay. So to make the conclusions like about the whole presentation, the first one I'm talking about the tensile test. Okay, and the tensile test that's giving the stress strain cost. The first thing that you are given about the elastic property of material by means defines a modular of elasticity and go to the elastic points, and there will be the yieldings giving the resistance to plastic deformation. And in these portions, there will be the dislocation motions, RCS dislocation or screw dislocations, and then giving to the highest tensile strength of the material, and then finally this was broken. Then I moved into the fracture mechanics, which is about the how the fractures could be occur by the increase the nucleation of the buoys, grow the buoys, and coalescence of the buoys, and then different kind of fracture depend on the different material, just like the ductile material or the brittle material binds seeing the nature of the fracture mechanics, just like the intergranular or the granular fracture. These informations are provided briefly in this lecture, and then I hope you enjoy these presentations. Thank you very much.